She's not wrong. We gotta know all the things all the time. All right. Everybody in here?
Yes.
Everybody ready to go?
No.
Waiting on Ian.
Yeah.
We're leaving without it. There's the bell. All right. We're going to start by talking about a couple of things with the project. So if you want, I think it'd be a good idea maybe to get out just a sheet of paper to write down some key ideas that I want us to pay attention to with these projects. So again, please do note, I've sent you the projects back with feedback. I made comments in the margins. So like I highlighted a region, made a lot of comments for a lot of people. And that's the normal thing for the rough draft because we got to learn how to write, things to think about. And so first things first, I want to talk about one of the big details that I noticed. Okay? So right here, this is your proficiency scale for this unit, right? On study design. These are the words that we should be using and then putting in context a lot. Like voluntary response bias, undercoverage bias, non-response bias. We were not using this language. When it came to experiments, I didn't see a single person talk about experimental units. Now, I did have people talk about subjects, which is good. But like, when we talk about the components of an experiment, we need to talk about the experimental units, we need to talk about our explanatory variables or factors, we need to talk about levels or treatments, our response variables, our confounding, and like, one of the things I want to emphasize, I want you to think about is define these terms. And not just like write out a definition. Charlie, can you help start out? Actually, you might be able to press on the door. Just push the door. I lied. Okay. Oh, Ian closed it behind him. All right. So we want to be using this language, okay? So don't forget that. Because part of this is a chance for you to show proficiency. A part of this is for you give you a chance to show proficiency with things you didn't necessarily show proficiency with earlier in the test on the unit. The other thing is to practice writing like how the AP exam would ask you to write. Remember, and this is where I would look at my Freire models, when you say something is biased, you can't just say, hey, it's biased. On the AP exam, I think they specifically say you need to indicate how that it might introduce bias, but then also would it over or underestimate the population? Right? One of the things that I do want to pause and I want to point out about the STEM study, and also, by the way, y'all need to make sure that you're looking at each other's papers and giving feedback so that you have the best article or analysis possible. But when it came to the STEM faculty study, when I looked at it, how many of the professors got the survey?
It was all of them who had been tenured.
It was all of the professors at the university at that school, right? In the STEM, right? Because that's in the STEM, right? Okay. Which students did they collect data from?
All the students in the class.
Okay, so hey guys, if you're using this word "all," the students and all the professors, they have the population. They have a what? Oh my gosh, guys, shouldn't we be talking about a census here?
Although it did exclude some students, mainly ones who didn't submit their race data or
Yep.
didn't complete the ACT recipe or whatever.
And that's a good point. Yeah. So I would still call it a census though, but we may clean the data because of missing data, right? I would still call it a census. We may clean the data a little bit because of missing data. But what about the professors?
Response, voluntary response.
Not a voluntary response.
They all kind of
Hey guys, I need y'all to remember with that STEM faculty, I think they only got a response from like half of the faculty.
Yeah, 40%.
It was 40-something%, that's right. If you're chosen to be a part of the study and you choose not to respond, it's not voluntary response, that is non-response. Guys, you need to be talking about how is the group that we got data from different from the ones who we didn't. At least come up with a hypothesis. And then, because there's such non-response bias there, you need to be thinking about what could the researchers have done to reduce the effects of that non-response bias. right? Like when you identify elements of bias that's going on, then you need to think about how would we reduce the effects of this non-response bias. When I looked at the study with the STEM faculty, and I look at the questions that were asked, I think those questions were fantastically designed to reduce one of these forms of bias. Anyone know which one?
Sampling bias.
Not sampling bias. Remember, sampling bias is when you sample, it's just bias in general, but one of those biases was reduced by the way they asked the questions.
Response bias.
Yeah, they specifically asked these two questions to not push people in a specific way. And they gave them a self-scaling system, a Likert scale is what it's called, to indicate if they strongly disagreed to strongly agreed with those statements, I think, was the language that they used. That reduces the bias, because I know a lot of us recognize the growth versus fixed mindset idea, but here's the thing. A fixed mindset, if you say it that way, has a negative connotation to it. A growth mindset has like this positive, happy feeling to it. So did they ever actually even use that language? They didn't. They intentionally didn't use that language. They reduced the effects of response bias by not doing that. There's more to this study than just those things. But, this is actually something I skipped, and this is something I wrote a note about specifically to talk about. Here's what I need us to remember. Everybody correctly at some point identified the fact that the STEM faculty was what type of study?
An observational.
Observational, okay? So we said observational, and a lot of us talked about correlation. And yeah, you can find correlation, not causation, in an observational study, but what is the goal of an observational study?
To provide an inference about population.
Hey guys, if you're trying to make an inference about the population, it's really hard to do that if you never define what the population is. Most of us never talked about what the population was. Oh. And I do want to put this out there at this point. This population, what would this population have been?
The students for underrepresented minorities.
So it's the university, specifically students and faculty in what? In STEM, right? Like, and we wanted to know more about the underrepresented minorities, right? URM, I think is the term they used. But here's the reality. And this is what I want you to think about. This is something maybe to consider when going to a better study. Do we really only care about the students and the faculty at that university?
No.
Is it necessary that that university represents all universities
No.
and all professors and students in STEM? So by just having data from that one university, what do we have?
Undercoverage bias.
Well, so we have what?
Undercoverage
We have undercoverage bias. We need, like, I need y'all to recognize that. Yes, but like, if we only get it from that one university, then I have undercoverage bias. Because I don't know what it looks like at other universities. I don't know what it looks like outside of the country. And so here's the thing, like, when we're talking about this and we're making inference about a population, guess what? That was probably one of the better inferences we could have made about that school, but I don't know much outside of that school. Unless we treat that school as a cluster, which I don't know that we can, and we have this non-response bias, we have all these other issues, right? So think about what could we have done? What could the researchers have done if they had more resources? And I gave you other feedback as well, okay? So think about that. Yes, Raina?
Would it be better than just having census on one full university in the STEAM field, or having like maybe less, not census, but having a lot of university data?
Well, that's my question. Like, legitimately, if we have data from that one university, I do know a lot about that one university, but do we want to know how fixed versus growth mindsets affect students at that one university or maybe across the nation?
Across the nation.
Like, personally, that's what I would want, is more what does it look like across the nation. There's ways to do stratified random sampling based on maybe the type of college or the size of the college, things like that. Or you can just do a simple random sample. But I will point out, if we're talking about observational studies, we're talking about inference about a population, we should always want to throw all of our framework, all of our analysis needs to go through this goal. All of your analysis needs to go through this goal. Okay? And then what's the thing that causes an issue with this? What prevents us from making accurate? And so one, I would redefine the population they looked at, but what is it?
Bias.
Bias, right? And so whenever we talk about the types of bias or the sampling methods, we need to run that through a frame of, or when we're talking about the study itself, how did they reduce bias, right? How did they do these things? And again, think about how you need to write about this for the AP exam. So going deeper with a lot of that. But everything needs to be run through this framework. This is the framework for the study. An inference about a population. Bias is the issue. The last thing that I want to point out with, which I was just thinking about it. I will say this. A census, yeah, it's great. Are you going to be able to do a census of all universities? No. Of all STEM faculty in all universities? No. So don't do a census. Like when you write about it, yeah, it'd be phenomenal if we could do a census and know the true population and all of that stuff. But think about the stuff that we have done, right? Think about what type of sampling you could do that might reduce the effects. Would it be best to do a stratified or a cluster or a simple random? I will tell you this, there's definitely one of those that's better than the others. You can actually even do a combination of them. You can stratify first and look at different homogeneous groups, but if you look at like all large universities, there's still a ton of those. But then I could do a couple of clusters for each size university, or public versus private, or things like that. Because like there's ways to stratify along that as well. Okay. For those of us who had the STEM faculty, does that give us a better frame of reference?
Well, sorry.
Go for it, Ian.
Well, I said, so like in our groups, they need to be reflective of the population, which is all colleges.
I don't have to be, but you need to at least define what the population is. And like, my argument would be, personally, I care way less about a single university as I do about what does it look like for all universities. That to me makes more sense, or at least maybe in the U.S., not just a single state or anything like that. Yes.
Also, I think with the underrepresented minorities, I thought that was like the whole point of the study.
It's to make an inference about a correlation between growth and fixed mindsets for professors and the response being the level of success for the underrepresented minorities. But you then have to compare that against non-underrepresented minorities. And do we only care about the professors and students at that school, or do we care about more than outside that school?
More.
So like it is a correlation, right? But the correlation needs to make an inference about a population, right? It's not causation, it's a population that we're looking at. So yes, we're looking at correlation, but we need to think about what's the big population I can make an inference to. At this point, I can only make an inference about that university, and even then it's a biased inference because I don't have all the professors, right? Okay. All right, for the doll experiment, I gotta go ahead and say this. That doll experiment was tough, guys. Like, if you really dove deep into that doll experiment, it was not an easy one. You can always come in and ask me more questions, but when we talk about the doll experiment, first off, what was the doll experiment, or since it's a doll experiment, doll test, what should we be thinking about? What's the major framework?
Causation.
Causation, right? Like, we're looking for causation. And so, everything you write needs to go to this idea of causation, okay? And thinking about, within that causation, how did we reduce confounding, right? Or how did the researchers reduce confounding? How could they better reduce confounding, etc., right? So this is my framework. Everything needs to run through the idea of causation. And so, how are we reducing confounding, okay? So, those are some big ideas there. Now, I do want to address this. We need to recognize, and by the way, everyone needs to engage in this because you all need to be thinking about this. You all need to be, in your small group, engaging in conversation about making this better. This is not, Ethan, which one did you have? So you have STEM faculty, right? And who was your partner again? Sophie, right? It's not you have STEM faculty and Sophie has doll experiment. You each wrote, but you need to be giving each other feedback to make your paper the best. Because, one, you're sharing a grade. Two, Sharpen iron, iron sharpens iron, right? You got to push on each other, make each other better. Okay? Help each other develop a better understanding of these concepts. And I'm going to credit to you both with understanding because you're both supposed to be working on this. Now, here's the thing with that doll experiment. I know that what they want to make an inference about is how society impacts preferences, right? And social or the racial identity. But I need you to think about that study. Did they ever manipulate society? No. What were the treatments? What did they manipulate?
The different dolls.
The different dolls. That doesn't sound to me like we necessarily can make an inference about causation, at least from society to racial identity and the doll preferences. Now, can we make maybe a prediction or say something about it? Yes. Like, we can to a certain degree, but it's important to recognize that how those children interacted with society was never manipulated in that study. It wasn't. It can't be. They did have treatments. They did have a look at like how racial identity impacts preferences. But there's more that they should have done to make a stronger argument. But the reality is we can never prove that the way those children are interacting with society is affecting things. Now, so think about that. Think about things they can change. It's tough. I will say this. In terms of an experiment, was it a landmark experiment? Did it change a lot? 100%. Is it a phenomenal experiment? Do I even come to the conclusions that they came to make the argument they did during Brown v. Board? No. Because I can't establish causation well there. Not going to lie. There is some causation that you can apply, but those things to think about. But here's what I want to point out really quickly. All of, this, right here. These things are known as the components of an experiment. You got to have these things. So you know what you need to define if you had this section? All those things. Like you've got to define the components of the experiment. On the AP free response questions, didn't you have questions about what are the experimental units and what are the treatments and all those things? Yeah, like you got to address those things. Down here, what are all of these? These are ways to reduce confounds, right? So these are the elements of a well-designed experiment. That's how we reduce confounds. You need to address these. Okay? Because there's a lot that the researchers did and did well to reduce confounds. Even though it's a little sketchy on the cause and effect, they did a lot of things really well in terms of confounds. Guys, I was blown away that no one talked about replication. How many kids did they talk to?
A lot.
It was like 270 kids. So what did they do with their experiment? They replicated. Does that reduce the effects of confounding? Yes. 100% yes. One of the most basic elements of an experiment, and I think one group did talk about this, maybe two, but was it ever clearly indicated that students were randomly assigned to the treatments? No. They never had random assignment to any treatments. In fact, I think the only technical treatments, was it switching the order that the dolls were presented in? Which that reduces confounding, but it doesn't really feel like a treatment to me. I think what might have been better, which this was interesting, direct control. They addressed early on that the questions were asked in a specific order because they found that when they asked about racial identity first, it impacted their responses to like what was their preferred doll, things like that. And so they directly controlled what direction the questions were asked. And so one, that should have been addressed as a way to reduce confounding. But also, and more importantly, I feel like they should have used that as one of their treatments and randomly assigned which order the questions were asked in. Like, to me, if you take the questions and you switch the order, so like there was 1 through 4 that established what they preferred, I think, is that right? And then 5 through 8 were about their identity and understanding. So like, if you randomly order this, then you get a look at how do they naturally think about the dolls versus how do they think about the dolls when comparing against their racial identity. That to me would get more to the idea of how societal pressures impact those children. At least to me, I think that that's a huge thing. In fact, to me it looks like either the experimenters didn't think about that factor or they were trying to tell a certain story and make it seem worse and only present data where it's like, oh, these kids, they're preferring white dolls over black dolls because of this, this, and this. And to me, I think that it tells that story, but I think it is a biased view of that story. Yeah, I think that's a big thing there. One person did a really good job of recognizing that it was a single blind experiment. Did the children ever have an idea of what that experiment was about?
No.
No. In fact, I think, look into it because there's a specific thing that they talk about to recognize those things. I think that some blocking would have been a good idea. There's a couple different ways to block. You could not have done a matched pairs in that case. Completely randomized is fine, but again, we have to have some kind of random assignment to reduce our effects of confounding. And then again, just think about how can we make this study better. But notice, I'm going back to like, what are the components of an experiment? What are the elements of a well-designed experiment to reduce confounding? And you can organize it the way you want. You can talk about all the elements that they did well and then a later paragraph of what they could have done better. You could talk about certain things that they did well and say, but while they did this well, what they could have possibly done was blank, right? Like, they directly controlled the order of the questions, and so that reduced confounding in this way, but there could have been this problem as a result. You could have changed this, right? So things that went well versus things that could have gone better. I'm going to look to see if there's anything else I want to add into this conversation tomorrow, but I think that's enough time talking about this right now. Hopefully this gives you a better picture of what I'm looking for, and I wanted y'all to work on this a little bit, but please note, like this is a little bit more, I think, than what some of us were originally thinking this might be. And it's not going to take me as long to to score it next time, because I don't have to give feedback next time. So what I'm thinking is, turn it in the Wednesday before midterms. Gives you a week and a half to work on this. But I'm giving you a week and a half because I want a week and a half's worth of time and effort put into improving this. So like, yes, you typed it, but I think that there's a lot that we may need to reread and rethink about to improve. Okay? By the way, if you want to ask questions, I'm more than happy to sit down and talk with people. Yes, Dixie?
When are the midterms?
Next Thursday, Friday, I believe.
So the weekend before midterms?
So next Wednesday
Next Wednesday?
is when they would be together. Okay. Yeah, so that's all I got for there. So think through those things again. Proficiency scales are driving what I'm thinking about and looking for. Let's see if there's any other small notes I wrote to myself. Yeah, all the writing needs to be run through the lenses of what was the goal and what was done to reduce bias or confounding. And again, something I would point out is addressing what bias and confounding are up front. It's like when you say, hey, this is an experiment, and this is why I know it's an experiment, they did these treatments to reduce confounding, and kind of using that as a platform to like really show me that you understand what confounding is, that's important, right? You have to, on the AP exam, not just say, hey, there's confounding here, or just, hey, this is bias. You have to make it clear you understand what those things are. So hopefully that will help get y'all back on track. And again, by the way, these scores are definitely way better than what they were last year and 2 years ago. But that's definitely still room for improvement, right? Like, I do this for two reasons. One, I want us to learn how to grow and improve. And two, because you are capable of amazing things, and I need you to take that feedback and show that growth, right? And oh, the other thing is also, all this shows up on the AP exam, and so like going this deep on it is going to help you prepare really well for that AP exam, okay? Okay, so independence recap, we got to do that quickly because we got 20 minutes till lunch, and dependent events, tree diagrams, wrap up, progress, check questions, and maybe some practice before DYU at the end of the day. All right, so do not forget conditional probability. Overall, what is a conditional probability? Like, what, not how to calculate, what is it?
Something given another.
Probability
sorry.
of an event
I'm
has
sorry.
to be given
Hold on,
by
right?
another.
Kenzie was talking. Let her talk.
Oh,
Go for it.
probability of an event happening given that I know there's already.
Right, so it's a probability that something happens, assuming or given that something else already happened, right? And so we looked at the idea that the probability of A happening given that B has already happened is what?
OP of A.
Okay, so it's the probability of both happening, A and B, divided by the probability of B. Now, here's the thing though, if they're independent, what is the probability of A given B? Okay? So it's probability of, oh yeah, that's A given not B, but more importantly, and what I always focus on is just the probability of A. If they're independent, B doesn't matter, it's just the probability of A. Alright? Now, I'm going to hold on to that, and I need you to hold on to this, because we're going to come back to this within that next lesson. Okay, so recap a couple of things. So what we need to do is, oh no, that's, so we're talking about independent events. Here we go. We need to know the general multiplication rule, how to use a tree diagram with dependent events. So first, how to determine if they're independent, but more importantly, how to find the intersection, A and B, or a union when given conditional probabilities. So, what? Intersection is and, union is or. I said both. We're going to do both of them. Yep. Okay. I don't know why I left this in here. Okay, so I want to talk about this tree diagram. So one of the things that Mr. Anderson and I talked about, that when I do a tree diagram, one, we got to know when to do a tree diagram. I'm going to talk about that in a second, and to see what y'all are thinking. But two, I never do a tree diagram like this. Let me clarify, that's completely wrong. I don't do a tree diagram just labeling stuff. Right here where it says probability of this is probability notation is going to help you so much when it comes to constructing a tree diagram. Use that probability notation to your advantage. So like, when I look right here, this first split, yeah, the first is red, the first is yellow, so that is the probability of the first one being red. That's how I would write that. And I would write that along this line. And so what is that probability of the first one being red? It was 4 out of 6? Okay? So like right here, we didn't use yellow, we used pink. So what's the probability of the first one being pink? 2 out of 6. Now, because we kept the starburst out, right? If we didn't keep that starburst out, what would the probability, so hear me again, if I didn't keep the starburst out, what would the probability of the second one being red given the first one is red? I was saying, listen to my question again. If they're if I put, no, you're not wrong. If I put the starburst back in, so if I didn't keep it out, if I put the starburst back in, what would be the probability of the second one being red given the first is red? It is 4 out of 6. Because remember, nothing's changed. If I put that that starburst back in, nothing has changed whatsoever. So it's 4 out of 6. But what did we do? We kept that starburst out. So do we still have all 4 reds? No, we have 3 reds. We no longer have 6 starbursts, we have 5 starbursts, okay? Now here, we had a red, that's it, that's given. And what are we looking at down here though? The probability of a pink, the second one being pink, given the first is red, so it is 2/5. Now, Mr. Anderson and I talked about this, and I want us to recognize this. What do these two probabilities add up to?
100.
5/5, 100 or 1. So what does that make this right here?
That makes that, any other one, not any,
Not just that, so it's a 2-word thing, both start with an S.
Sample space.
That's my sample space, which is weird. There's lots of sample space going on. Dixie's like, what are you talking about, Mr. Kenny? Right, remember, if I have a sample space, I have everything, right? Okay, so assuming the first starburst is red, what are the 2 options? The second one's red or the second one is pink. That is the sample space within the condition of the first one being red. That's why these add up to 1. Notice, what do these add up to?
1.
Because on the first draw, this is my sample space. Down here, I have the probability of the second one being red given the first one is pink, and that was 4/5. And the probability of the second one being pink given the first one is pink, and that was, notice what do these add up to be? 1. 5 out of 5, or 1. So we have another sample space here. It depends on what is happening. Here we have these conditional probabilities, and so we have these miniature sample spaces. I'm talking about all this for a very specific reason that we'll get to in a second. Now, I want to pause before I get back to here. The probability of the second one being red given the first one is red. If I didn't give you this tree diagram, how would you calculate this probability using a formula?
Just get individual volumes and multiply.
Isn't the probability
Oh, and-
probability
of R2 and R1 divided by R1?
Notice it's the probability of their intersection divided by that condition, right?
I think that we did it in the number 6. Is that the same one?
Say that one more time.
Is that the same thing that we did on the number 6?
Partially. So notice right here, if I take the probability of R1 and I multiply it by this conditional statement, what do I get?
R and R.
The probability of,
R and R.
so 2 reds, right? The second one being red and the first one being red. So you notice if I take the probability of red 1, or the first one being red, multiplied by the probability that the second was red, given the first one's red, that gives me that intersection right there. We talked about at the end of 5.5, there's a name for this. This is the general multiplication rule. Mr. Anderson also talked about this, I think, at the end of this lesson, right?
Yeah.
Okay, so general multiplication rule. So notice, when I multiply these 2 probabilities, that tree diagram is giving me the probability of 2 reds. Isn't it? It's wild. I'm going to leave it as, was it 3/15 when we simplified? Hold on one second.
No, that's 6.
6/15. Thank you. Say again. Say it one more time. It can, but I'm holding on for a reason.
But
Okay.
the one on the board.
So notice, hey guys, right here, if I take the probability of the first one being red and multiply it by this conditional statement, what am I going to calculate? Because this is the same as this condition, I'm going to calculate the probability of the second one being pink and the first one being red. So when I multiply these, 4/15. So when I take the conditional probability and multiply it by its condition, I get the intersection. When I take a conditional probability and I multiply it by the condition, I get the intersection. That's what that's really saying. Condition times the conditional gives me the intersection. And so it's important to understand this framework. I'm going to talk about another detail with this in just a second. 4/15. So this tree diagram allows us to go from conditional probabilities to intersections like that. Notice, what's the sum of all those probabilities on the right-hand side?
1.
Sum is 1, right? Because those are all the different ways to draw two starbursts. And so that's a new sample space. So there's different sample spaces going at the same time. So big idea to understand is when we multiply across the branches in a tree diagram, what's it going to calculate?
The condition, the intersection.
The intersections. Multiplying across a branch in a tree diagram calculates intersections. Yes,
Is
Ian?
this the same thing as the general multiplication rule for independent events?
General multiplication rule works for independent and dependent events. If they're independent though, that's just probability of A times probability of B. That's different. Yeah. Yes, Dixie.
So, how would you like do it in reverse? 'Cause I was looking at the book.
And that's what I was going to talk about. Yep. So first things first, I want to point out, what is a tree diagram all about? Like what's kind of like the main probability that is really heavily involved in a tree diagram?
Conditional probability.
Okay, tree diagrams are great for conditional probabilities. When you want something. What do we want? When you want intersections, yeah. So it's not every time, but if you want an intersection, man, that tree diagram is fantastic. Like that's what we want to recognize out of a tree diagram. It's great for conditional probabilities when you want an intersection. Now, yes ma'am.
Is it correct if we can only use tree diagrams independent?
No.
We can, but.
You can use it in independent
but
events.
we don't-
It's just not necessary.
So, it's not necessary, but would it be okay to say that tree diagrams are good for dependent?
Yeah, tree diagrams are great for dependent events. If they're independent, you can just do probability of A times probability of B times probability of C, etc. Okay, so, go ahead. Yeah, we're going to talk about that in a second. So hold on. Okay, so really quickly, I do want to point this out. Number 6 here, so this is what you're asking about, Dixie. Number 6 says the probability, what is the probability that the first candy was red? So, red for the first one, given that we won the game. Right? Number 6 at the bottom of this?
I'm trying to find it.
Oh, gotcha. I'm sorry. So here's what I want to point out, and this is one of the best cases for using tree diagrams. So right here. Our original condition was either drawing a red or drawing a pink first, right? Notice, is that the condition here? No. What was the condition is no longer my condition. What was the condition is now the probability that I want. And the conditional or the end result over here is now my condition. So that's the idea of the conditional switching, right? So what was my condition is no longer a condition. That's where I want a tree diagram, okay? Because now when I look at this, and I'm still going to go to my probability formula, right? Okay, that's the probability of the first one being red and winning, divided by the probability of winning. So notice I've used my conditional formula, right? Written out that intersection, but I actually don't know either of those things from the beginning of the problem. But where can I find the intersection of the first one being red and winning? From where?
Multiplying it out.
From at the very top, right here. Right? It has to be red, the first one being red, and this is the only place that I win. So that intersection is 6 out of 15. Divided by. But that's not the only way to win, is it?
Oh.
Where else is there a place for me to win?
On pink.
On the very bottom when they're both pink, right? So this tree diagram, and I showed Mr. Anderson that something called Bayes' theorem. It's awful, right?
Yeah.
So there's this thing called Bayes' theorem that you can do completely algebraically, but it's absolutely horrendous. Like it's what I had to memorize, and kind of maybe halfway figured out in high school, and then still struggle with it in college, or I can just look at a tree diagram, right? Because what's the probability of winning looking at those two branches? 7 out of 15. Yep. Did it just for you, Star?
Is that why you kept it?
No.
Wait, I have a question.
67.
Yeah.
Why did you, where'd you get 7 from?
So right here, you can win up here, right?
Mm-hmm.
You can win right here. And so we'll point out this. So I could win by getting 2 reds or 2 pinks, which
Right.
is that union, right? How would I find the probability of getting 2 reds or 2 pinks? I would add them. But do I need to worry about their intersection at all?
No.
And subtract that out? No, because these events would be what? They're mutually exclusive. You can't get 2 reds and 2 pinks at the same time.
You can't.
So, because they're mutually exclusive, I just add them together. So what's 6/15 plus 1/15? 7/15.
But why did you divide 6 divided by 7?
Well, 6/15 divided by 7/15 is times 15/7. Right? So the probability of their intersection divided by the probability of winning. Does that make sense? What do you...
No, because I don't, why did you do like the first probability divided by the sum of the probabilities?
So this is, right here, this is when we have the first one being red and we win because there's 2 reds. You good with that?
Yes.
So that's this intersection. The first one's red and we win. That's this probability right here from that tree diagram.
Oh wait, I get it now, it's the formula. Oh, okay. Okay, I see what you did there.
There you go.
Okay.
All right. And then, Mr. Anderson, you talked, I think, at the end of last week, is the probability of at least 1 red. Okay? So, one of the simple rules, but important rules that makes things way easier a lot of times is, I could get a red here, or a red here, or a red here. And so you could add all those probabilities together, right? But Raina, what did you talk about at the end?
Huh?
You don't remember? Yeah.
Oh, did I talk about it?
Yep.
Yeah, subtracting
The probability of at least 1 red happens in each of these 3 branches, but right here, I don't get any reds, right? So if it's at least 1, it's the same as 1 minus the probability of none. That way I only have to look at this 1 branch. So we know that the sum of all these probabilities has to be 1, so 1 minus the probability of none.
It's
Gives me
14
at
out of
least
15.
What?
14/15?
Yeah.
Yeah.
Well, yeah, 1 minus 1/15. That's easier than adding all those up, especially if we have more branches. Okay? All right. Hopefully that helps some things. We're going to do this check your understanding, and then progress check. I'll start the check your understanding before lunch. We'll finish it after lunch. But here's what we want to recognize, because right here, this question in its setup tells me instantly make a tree diagram, even without them asking me to.
Yes.
Because right here, 22% of them have the flu. So the probability of flu is equal to 0.22. Please hear me very clearly on this. This isn't me just knowing this problem and doing this. This is literally what I did when I started talking about Mr. Anderson, is I read that statement, and so I wrote out a probability statement. That tells me a lot of what's going on. Okay, so the probability of flu is 0.22. What's the probability of no flu?
0.78. 0.78.
Okay? Next, the rapid flu test will incorrectly give a negative result. So this is the probability of a negative for 3.7% of the patients who do have the flu. So that's not of all patients, that's only the ones that have the flu. So the probability of getting a negative test on the condition that you have the flu is 0.037. For those of us who have done medical stuff with HOSA, what do we call that event where you get a negative test even though you have the flu?
But false.
False. Well, it's a false.
False positive.
That's a false negative.
That's what I meant. You gotta.
Okay. So we want to recognize that. So we actually know something else. What is the probability of testing positive given you have the flu? 963. Okay. Then the probability of testing positive given you don't have the flu. So I'm going to finish writing this and then we'll pick up here after lunch. Notice this probability of a positive result if you don't have the flu, 0.026. All right, head on lunch. We'll finish using this after lunch.
Appointment.
Okay. So
So you're gonna be out today.
really quickly, I just want to point this out. Thank you. So again, please notice as I'm reading through this. Yes. Oh yeah, that's fine. As I'm reading through this problem, I'm writing out these probabilities, and this is as soon as I see all these conditional probabilities, and also here's a big thing. Notice how these conditions match this up here. That tells me a tree diagram, right? So I write out my probabilities that use that to say, tree diagram. Even if it doesn't tell me that, tree diagram is a great option here. Probability of flu, 0.22. Probability of no flu. Thank you, star. Probability of testing positive given that I have the flu. Way to lie to me. So false negative, 0.037. By the way, once again, I do want to point out for those of us who missed this before, do I ever put the probability inside of the parentheses?
Never.
No, that's the event. The outcome is the probability.
Y value.
And this to me just helps a whole lot in visualizing what is happening. And then I have to remember, it's going to come up in a second, I'm sure, that when I multiply across this branch, that gives me the intersection, right? When I take the conditional probability, multiply by the condition, I get that intersection. But that tree diagram summarizes all that information really, really, really well. So notice, what does number 2 ask?
Find the probability that a randomly selected patient gets a positive result.
So probability of testing positive. How many different ways does that happen?
3 times.
There's 2 branches. The very top one?
And the bottom. Oh wait.
Very bottom? No.
What about the one right under it? Oh, testing.
That's testing negative,
Oh.
given you have the flu. We're asking just what's the probability of testing positive,
Okay.
right? And so remember, when I multiply, I'm not going to write out all my notation, but when I multiply it, it gives me the intersection. So 0.22 times 0.963 plus, I was just going to do all this. So notice, if you write this whole thing out, you can put that whole thing into the calculator all at once. Okay? This would be enough work for the AP exam. And especially if you do that tree diagram with those branches circled.
You mentioned that in the good time to use tree diagram is when the values match. I didn't completely get that.
Well, so when the conditional probabilities and you want the intersection, because right here also, if you can take the conditional and multiply it by the condition, that gives you an intersection from that general multiplication rule. So when I do this conditional times the condition, then that gives me the probability of the intersection.
How do you know that it gives you the intersection? Can you just calculate them and know it?
The general multiplication rule. So remember, we had probability of the first one being red times the probability of the second one being red given the first one is red. That was the intersection divided by the condition. So when I multiply both sides by the condition, it gives me the intersection. So that's what we're doing here. We're taking the conditional, multiplying it by the condition, so we get the intersection of those 2 events. Okay, so what do we get as that probability? A little over 0.22, right? 0.23, what? 214. Okay, so 4 decimal places is usually what we want. Yes, ma'am. Oh, yes, Phoebe, yeah, your hand up.
So, do we have to would the free response question ever ask you a question?
Will it ask you to construct a tree diagram?
Yeah, or
No, you need to recognize to construct a tree diagram.
would it be graded like that, like if you don't have it, or versus if you?
Say it again.
Like, would it, would it ever like be part of the grade? Like, grade?
No, but it'll be, like, you always have to show work, one, so evidence of understanding, that's part of the work. Two, most of the times it's going to help you see what to do. So I would always do it if I have that idea at play. Dixie, was that you raising it?
Why did you multiply and then add it?
So remember, this is the probability of testing positive and having the flu. This is the probability of testing positive and not having the flu. And so we had to put those together to get all the ways that we test positive. So remember, that was these two branches, that's why I circled them, those are the two branches that have testing positive. So I would add those two together. They're mutually exclusive, so I don't have to worry about the intersection. Number 3, if we select 4 patients at random, what's the probability at least one of them gets a positive test result? Number 4, or 3.
You just have to multiply, add all of the probabilities.
Yeah, which probabilities?
The resulting ones.
So all 3 of these?
All 4. Wait.
Positive.
So what we need to recognize is, this question is not actually based on this tree diagram.
Yeah.
Wait.
This is a single patient. This is the probability that that single patient has the flu or does not have the flu, that they tested positive, given they have the flu, etc. What this is actually looking at is patient 1 either test positive or test negative.
Is it 0.96 union? Or I guess not.
Person 2 can either test positive or negative. Person 3 can test
Positive or negative?
positive or negative. So notice how we're getting a whole bunch of branches. Because each of these, so like there are 8 different ways so far to have 3 patients testing positive or negative. So I'm going to read. So we need to recognize that this is a little bit different. Now, please don't write this out. I'm using this to illustrate something.
Yeah, we don't need tree diagrams for this one.
You just do 2 to a power.
Not 2 to a power 4. Well, that tells you how many branches we have. It would be 2 to the 4th to just show how many branches.
Bless it.
Bless you.
Bless
you.
But, okay, so notice these are all based on person 4. These are all based on person 3. Okay, I'm just trying to help you visualize it. But whether person 1 is positive or negative, person 2 could be positive or negative off of each of those. Positive or negative off of each of those. But here's the thing to remember. If you have people coming into a clinic, and them having the testing positive or not, will one person testing positive affect the next person testing positive?
No.
No, so what would we call these events? These are actually independent events, right? So the probability that the first person tests positive is,
0.963.
no, 0.2321.
No.
That was the whole point of this. Those are all the ways to get testing positive. That number you were talking about was the probability of testing positive given you had the flu. That 0.963. That's probability of testing positive. What's the probability of this person testing positive? Same thing, and this one,
Same thing.
and this one.
Same thing.
Okay? But we need to read this, because here's the thing. This branch has at least 1 positive, 1 positive, 1 positive, 1 positive. It's a whole lot of positives.
Yes.
I don't want to add up all those branches. It'd be 16 or so branches total there. So what can I do?
Multiply.
A formula.
There is a formula. Subtract what?
Subtract the ones that's only negative.
Oh, subtract the ones that are only negative. I want at least 1 positive, right? If we select 4 patients at random, what is the probability that at least 1 is positive? Does anyone see any branches where there's not at least 1 positive?
Just the bottom row.
Just that bottom branch. That's the only one, right? So then all these others, plus this one, have to add up to 1. Or 1 minus the probability of none. They're independent events, So 0.7679 times 0.7679. How many times am I going to multiply that 0.7679?
4
4
times.
times, which is 0.7679 to the fourth. Guys, if you see the probability of at least one, yes, you can add up all of these, or you can just do 1 minus probability of none. It is always going to be easier to do 1 minus probability of none. Okay?
Did you get the 0.7679 from a minus? Yeah.
Yeah, probability of testing positive is 0.2321. Thank you for asking that. So the probability of testing negative has to be 0.7679, right? Because those have to add up to 1. Good question. Yes, Phoebe.
I don't really understand why you went from what, like 2 outcomes for first, like the first person and then 4?
It's not 4 for the second one, okay? It's that if the first person tests positive, then the second person can test positive. First person's positive, the second person's negative. Or if the first person was negative, the second person is positive, negative, and then negative. It's because we have 2 sets of 2 that I now have 4. And then here I have 2 sets of 4, so I would have 8. 2 more sets of 8, so I have 16. Does that make sense? Yeah. So it's that branching
Wait,
effect.
can you
Yes,
explain where 0.76749 comes from?
if the probability of testing positive is 0.2321, probability of testing negative is its complement, 1 minus that. These have to add up to 1. You either test positive or you test negative. So the probability of testing negative is 1 minus the probability of testing positive.
Oh, okay. So
And so remember, in part number 2, we calculate the probability of testing positive. I need the probability of testing negative. Yes, Raina.
I still don't get that why you went raised to 4th power.
How many patients are we looking at?
It doesn't.
Yes, it does. Number 3, how many patients? 4 patients. And these are independent events, right?
Yeah.
So we want the probability of negative and negative and negative and negative. So 0.769 times 0.769 times 0.769 times 0.769 because they're independent events. If they're independent, we can just multiply the probabilities.
Oh, I think I was confused because I thought we were in number 2.
No, we're on number 3. At least 1. Remember, this was number 2. That was probability of testing positive. Was this? We're done with that. We're using that to find the probability that at least 1 is positive. It's 1 minus probability that none are positive. All right. And then, Dixie, I think this also goes to part of your question earlier. Number 4, and I don't have time to finish this, but given that a randomly selected patient is positive, notice what probability of the condition being positive. So given that someone is positive, how likely is it that they actually have the flu? So notice, Dixie, how originally my condition was flu, but now my condition is positive. What was the condition has now become what I'm really looking at with the testing positive being my condition now. And I don't have a probability of testing positive originally. I have to find it. And so that's what the AP exam will often do, is they'll have you find this first, and then you will use that down here. But notice the tree diagram helps me see both of the ways to test positive. These are the 2 ways to test positive. And so that's how I know. So the probability of testing positive for the flu and being positive will be these 2 multiplied. Testing or having the flu and testing positive divided by that probability from right here. Because remember, those are the 2 ways to test positive. So when I see what was my condition be the first part now, and my condition change, that's when that tree diagram is going to help me see those 2 pieces and bring it all together. Okay. All right, I'm going to have to continue to talk about the progress check. What I think I'm going to have to do is we're just going to have to go through progress check, do some practice in class today, and start tomorrow with the DYU, I still need you to turn in the Frere models today so that we can start tomorrow with DYU, immediately go over it. So that's what we'll have to do. All right, so progress check. Here's the questions that I saw that I needed to talk about. This is number 12 off of progress check A. For number 12, it says a survey of people on pizza preferences indicate that 55% preferred pepperoni only, 30% preferred mushroom only, and 15% preferred something other than pepperoni and mushroom. Suppose one person who was surveyed will be selected at random. Are P and M mutually exclusive events?
Yes.
So when we think or we see that term mutually exclusive, what do we immediately need to think?
And equals 0.
The probability of P and M
Equals 0.
equals 0. Well, how could I figure that out here?
Because you know,
Additional-ish.
all of those variables in there, they equal 1.
So not the variables, but those events, the probabilities add up to what?
1.
1. Hey guys, if the probabilities add up to 1, what's the probability of the intersection?
0.
0. There's nothing else happening. Right? So that's all we need to recognize there. When we see the idea of mutually exclusive, it is the intersection, which is also called a joint probability. And so we need to be thinking about that idea of equaling 0. So yeah, the joint probability was equal to 0. Okay? So that was a higher miss question, but that's what we need to recognize. Okay? Number 15. This was the other really highly missed question. Did I put it?
Oop, missed that one.
Yeah, this one was a little all over the place. Okay, so let's read through it. At a large high school, 40% of the students walk to school. Again, this is what I do every single time I read a probability question. Probability of walking, 0.4. 32% of the students have been late to school at least once. Probability of late equals 0.32. 37.5% of the students who walk to school. So wording it this way makes this a what? A conditional, right? A given. So the probability, so given that they walk to school, so of the students who walk to school have been late, that is equal to 0.375. One student will be selected at random. What's the probability that the student selected will have been late to school and walk? So probability of late and walk. Okay, so what formula should we be thinking about?
Times time.
What?
My bad.
The probability.
Okay, so you can memorize the general multiplication rule, but I want y'all to hear me very clearly on this. I do not memorize extra rules. The general multiplication rule is built out of what equation? The conditional. So I'm just going to set up my conditional equation, or my conditional probability. The probability of late given walk, okay, that would be probability of late and walk divided by the probability of walk. See, they gave you extra information here that you didn't actually need. You didn't need this one. Notice 0.375 is equal to the probability of their intersection divided by 0.4. Notice I can memorize an extra equation if I want, or what would I do to solve that equation? Times 0.4. Yeah. If I see a condition, and this is again why I write out all my probabilities. Because when I write out those probabilities, I can easily see what formula to write it into. So when I see that, that tells me exactly what formula to use and what is necessary, what's not necessary. So what's the final answer?
0.1.
Okay, 0.15. Okay. I mean, there's other ways to do it. That's just the easier way to do it for me. I will also point out, could you have used a tree diagram?
Yeah, but I don't want to do it.
Yeah, I wouldn't either. But I will say, notice if you do that, you have to use walk as your condition. Right? So probability of walking, probability of not walking. You have to realize that that's the condition to start with. And there is some benefit to this. Because now I can clearly see to just multiply those. Tree diagram can help as well. Alright, I need y'all to pay attention to this one. This has actually shown up a couple times on multiple choice for the AP exam, and so we want to make sure we know how to do this. given independent events A and B such that the probability of A is equal to 0.3, probability of B is equal to 0.5, which of the following is a correct statement? So, does anyone know what the most commonly put incorrect answer
It's
was?
definitely not zero.
I got them all wrong.
Most?
I got you.
People put that. What is it?
E.
If they're independent though, what would that need to be?
A different number.
I put E.
No kidding. Probability of A given B, if they're independent, would equal
Oh, just A.
probability of A, right? So that is not what that says. That being 0 would mean their intersection is 0. This would mean mutually exclusive. The only way for this to happen is if A and B is equal to 0. That is not the case. At least they don't tell us that, right?
Right.
Okay, what would the probability of B given A have to equal?
Just B.
Just B. So that one's out.
B's out too, I guess.
Which one?
E.
E is out. Well, that was the most common
Yeah, that's fine.
incorrect answer, or second most common, one of the two. And then C has to be out. So the question I'm sure many of us are asking, like, how the frick do you get D? Tell me this. When I see probability of A, union B, what should you immediately think about? Okay, you add, okay, but it's not just that. So it's probability of A plus the probability of B, but is it always that?
No, it's minus A.
Minus their intersection.
Oh.
Oh. Oh. What's the probability of A?
3.
0.3. Probability of B?
0.5.
How in the world am I supposed to get that intersection?
Times. It's because they're individual.
They're independent.
0.
It's like
Remember, when they're independent, the intersection is just A times B.
Chad does not do
It's very commonly missed one. I assumed I would have to talk about that, but I'm not going to front. Huh? Okay. Just what I will point out about this is, once again, I need y'all to hear me on this. So when we see our conditionals, we need to know that's probability of B, that's probability of A, which is not what those say. It's not going to be 0 again, it's going to be the probability of A. So we're down to D and E. And so when we see our union, we've got to think our general addition rule. Remember, that's given on the AP exam, the formula sheet, right? And I will point this out, even if you didn't remember this part, should you just assume that the intersection is 0?
No, because they're mutual.
Right, it doesn't tell us they're mutually exclusive. It says nothing about mutual exclusion.
Yeah.
Yeah, so it is important to remember that they do tell us these are independent events. And if we're looking at independent events, the probability of their intersection, just A times B.
Well, how would it be if it was dependent on again?
If it was dependent,
Yeah.
you would need the conditional probability times the condition. They're not going to do that to you, because you don't have the conditional probability. Who started to raise their hand?
I didn't, but I'll ask a question.
Go for it.
Okay, so what does an intersection of 0 mean?
They're mutually exclusive.
Okay, wait, I think my question was, why is it 0?
Because they don't happen at the same time. Remember, the whole idea of mutually exclusive is that A and B don't intersect. So like, if I ask you, hey, what is the probability of rolling an even number on a die? That's over here, right? What's the probability of rolling an odd?
The same thing.
But, do they ever overlap? Do I ever have an even and an odd?
No.
Never.
So what's the probability of them both happening at the same time?
0.
0. That's what that 0 means. They cannot happen at the same time.
Perfect.
Okay, the second one that a lot of us missed, while investigating, so again, I want to point this out.
There's too
So,
many steps.
huh?
There's too many steps.
Not too many steps.
I got lost.
Like, I know. But you know what you could do to help you not get lost from the jump?
Maybe write it out.
Maybe write out some probabilities. Yeah. Because I agree, there's a lot going on here. Alright, so while investigating customer complaints, the Customer Relations Department of Sonic Air found that 15% of the flights arrived early. So the probability of early is 0.15. So immediately I go ahead and do its complement, because man, that shows up so often.
0.85.
Alright, 25% arrive on time. Ooh, okay, I don't want early complement. So on time is actually 0.25. So what is late?
0.6.
Point.
6?
Yeah. So that to be
Then you go
independent, right? Or mutually exclusive events,
Yeah.
right? Okay. So then we're also told 65% are overbooked. So the probability of overbooking is 0.65. 72%,
Or late or not.
so probability of late or
Union,
not overbooked is
72.
0.72.
Oh, to the intersection.
One Sonic Air flight will be selected at random. Was the probability that the flight selected will be late and not overbooked. Whew.
Right?
I got a whole lot of stuff going on here. You're right. So, what might be able to connect some of these probabilities?
General addition.
General addition rule, right? I see a union down here. I see an intersection over here. All right, so the probability of late or overbooked, not overbooked, is the probability of late plus the probability of not overbooked minus their intersection. Yeah, that is definitely not something I would have ever seen just reading that problem, but writing out the probabilities
Helps a lot.
makes it a little bit easier. I never would have made that connection without writing out those probabilities. So, write out your probabilities. When I see a union and I see an intersection, yeah, general addition rule. Okay, so this was 0.72.
Correct.
Probability of late we already identified as 0.6. Probability of not being overbooked would be what?
3.5.
Yeah, because remember, that overbooked is 0.65. Minus the probability of their intersection. Man, I only have one thing that's unknown. Let's go. That's good.
9.5.
Okay, so 0.95. So I'm going to subtract 0.95. Yep, that looks good to me. So it'd be 0.23. So you're right, there's a lot going on here. But you write out those probabilities using your probability notation, you might see something you didn't see before.
I got the time to do that.
You have 2.25 minutes per multiple choice question. And some of them will go like that. And some of them will take a little bit longer. Yes, Phoebe?
So I got confused because I thought like the late and like or not overbooked was like you just have to subtract 0.6 from that.
But did you write out that formula? Does that formula lay it out so that you don't misunderstand that detail? Like just, like, if I see a union, I think general addition rule in general,
Oh yeah,
Chat, why not get it?
right?
that's why.
If I see a union, I think general addition rule in general. You can also do it as a Venn diagram. Because what you're trying to find is this, right? And you know this is the 0.6, yeah, 0.6. You know this is the 0.35. And you know all together is that 0.72.
That makes it look a lot better.
That's another way to visualize it. So Venn diagram can make it work. I like the formula though. Okay. I think that was it. Yeah, that was it for the progress checks. We got 18 minutes of class left. Yeah, no shot to do the DYU. Sorry, I'm looking at all these. Okay, so really quickly, I think we have some of this in the practice that I have planned. So I'm going to leave this for y'all for homework, and I don't think I have this answer key yet. So as soon as school is over, I'm going to do an answer key for this. Yeah. So I'll send out an answer key so you can check yourself. So probability problem solving review. This is at the end of the unit lessons, and it's going to give us some good practice. So I'm going to give you all probably 5 minutes at a time to get as far as you can within these, and then we'll go over them. So let's work on this at vertical surfaces, give you a chance to get up, move around a little bit. So let's go 5 minutes and then we'll talk, and then we'll go 5 more minutes and then we'll talk. It is right there. Found it. All right, so number one, what's a good strategy for this one? Okay, so Venn diagram. When I see counts, I think Venn diagrams are good. Okay, so Venn diagram would be a great option here. What's another option that some of us chose?
Formula.
General addition formula. right? So when I see those counts and I see an intersection and I see a union, Venn diagram, general addition, great way to do it. Both of those are valid options.
Oh, where am I going?
Okay? So I just wanted to address that. I think we all got the right probability of 22 out of 25, just be careful. All right, number 2. A bag contains 3 red balls, 4 blue balls, and 5 green balls. If 2 are drawn at random without replacement, what is the probability that both balls are blue? Best option here.
Tree diagram.
Tree diagram is really good for a lot of people. What else is an option?
Or, formula.
Formula, right? The conditional probability. Now this one does require a little bit of thinking. If you use the formula, I think the tree diagram definitely makes the most sense. But the probability that the second ball is blue given the first ball is blue is equal to the probability of their intersection, which is what we want, divided by the probability of the first one being blue. This is the way some people did it. So the first one being blue, 4 out of 12. Probability that the second one is blue given the first one is blue is only 3 out of 11, because we would only have 3 blue balls and 11 total left. And then you multiply. So that's how you can use the general addition rule. I do think the tree diagram is your best bet here. Okay? I know a lot of us didn't get a chance to even start looking at this one, but I do want you to go ahead and start thinking about this. A company has 2 factories, A and B. Factory A produces 60% of the company's output, 5% of its products are defective. Factory B produces 40% of the output and 3% of its products are defective. If a randomly selected product is defective, what is the probability it came from factory A? Just gut instinct, what do you think?
Tree diagram.
I'm definitely going tree diagram here.
Sorry.
Why did you say tree, Charlie?
I'm just thinking, like the point the ball in.
Yeah, we need to recognize right here, the probability of defective given A is equal to 0.05. Whereas right here, if it is defective, so this is the probability given that we are defective, what's the probability it came from A? And so notice, classic example again, Dixie, of the condition swapping, right? Because like what we were given is defective given it came from A. Now we want to know what's probability it came from A given that it was defective. So tree diagram is a huge thing here. Conditional probability, huge thing here. So let's do this. It'll help you prepare for your DYU tomorrow. Do not work all these problems out. But I want you to look at each problem and figure out what strategy do you think you would use. So just what strategy? Think through that. Write that down. Maybe come up with a reason for that. Please hand me your Frere models before you leave. Sorry, I just remembered that, Charlie. You have it? No? Okay. So Frere models before you leave, so I can give you feedback before your DY or before your test. Frere model. Thank you. Thank you.
Oh, wait.
It's not on the note. No, just kidding. It's on there. This time, Brandon will actually give it to me and not gaslight me.
That was so funny. That was so embarrassing. That was not funny.
No, it was funny right now.
Surely you know what gaslighting is. It's when you make someone think that they did a thing when it didn't actually happen.